I think we're about ready to dive into it. So thank you again, everybody, for coming. We appreciate your interest in geothermal, as the education portion is very important to get out right now. There's a lot of information going around about heat pumps and about moving our grid to a more electricity-centric heating systems. Geothermal is one of the main ways we're going to be able to do that. And as we'll get into in the presentation, there are a lot of differences between the different types of heat pumps that are out there. So we're going to do our best to clarify that information and dive a little bit deeper into the energy transition that's going on in New York State right now. So thank you again, everybody, for attending. And if at any time you have questions, please feel free to put them in the Q&A portion. Alrighty. So, NOCO Geothermal 101. Let's get into it. So starting out, we have NOCO ourselves being a 90-year Western New York energy supplier. We started out in coal back about 91 years ago now, moved into fuel oil and then propane, natural gas and electric, and all the way up to today, we're offering solar, geothermal, wastewater treatment and remediation, environmental recovery, forestry, compost, bug proteins, LED lighting, and more. So we're making a big push into the sustainability market. So this is taking us from being just a fuels provider to a full service energy company, including the management and distribution of energy at your home or business. So some of those services include, like we just talked about, fleet fueling, propane or heating oil fueling and fill-ups, natural gas and electric rate managing, LED lighting. I think that's actually one of the more impactful images is the before and after of installing LED lights. It's not even just about the energy savings, which are pretty substantial, going from incandescent or a less efficient bulb to LED, but the quality of light is also a lot better. So we're more than happy to do lighting consulting and replacements. At this point, we're also offering generators. And on the right side of the screen, you can see Shanner Electric Showroom. So NOCO does own Shanner Electric now. We're more than happy to outfit your existing home, business, or new build with lights or all the electric equipment that you may need. Getting into the organics a little bit, we're doing composting and organics management. So figuring out how to take waste out of the landfill and turn it into something useful. So obviously with organics, we're able to do compost and different types of feeds for chickens and reptiles. But we're also able to do fuel recoveries or remediation. So if there's an oil spill somewhere, if hazardous waste is collected at any sort of facility, we are able to come pick it up and safely, transport and remediate it in an environmentally friendly way. So that is the NOCO suite of environmental services right now. And you can see on the screen a list of some of our bigger logos for partners. We are an energy supplier to a lot of Western New York, but our services go a lot deeper than that. I think that's reflected by a lot of these great groups that we have partnerships with. So why are we making such a big energy transformation right now? Well, again, moving from coal to heating oil to propane, NOCO's always had a history of moving to a more efficient fuel source or a more efficient way of using, utilizing, or distributing energy. So this is no different. We're moving into just a new field right now, as we've done multiple times in the last 9 decades. And this one's really exciting because of what we have going on in both the energy world and the political landscape right now. So let's get into what geothermal actually is, how it works. And again, if anybody has any questions, I'm more than happy to answer them. So geothermal systems do use the heat of the Earth's interior. However, they actually use the heat that's stored in the Earth's crust more than the heat that comes from the Earth's core. Now, what I mean by that is there are 2 forms of geothermal that people are familiar with. There's geothermal energy production, which is going thousands of feet deep into the Earth, thousands and thousands. In order to get the intense temperatures of the Earth's core, once we can reach some level of the Earth where that temperature is emanating out, We can put water into the borehole. It creates steam from those intense temperatures. The steam turns turbines and then creates energy. So that's geothermal energy production. Geothermal heating and cooling is going as little as 4 feet deep to as deep as 500 feet in order to utilize the stored solar energy in the Earth's crust as a heat sink for heating and cooling. So again, to make that distinction, geothermal energy production is going thousands of feet deep to create steam, turn turbines, and create energy. Geothermal heating and cooling, which is what NOCO is doing, is only going a few feet to a few hundred feet deep to get those near constant temperatures of the Earth's crust to be a heat sink for our heating and cooling systems. So again, geothermal is not making energy like a solar system is doing. It's utilizing energy. And it does so in a more efficient manner than most heating and cooling systems. And we'll get into that math a little bit later on. So to start out with just the physical system components. On the left side of the screen, we have the super basic workings of any heat pump, which is the refrigerant compression process. This is where you take low temperature, low pressure vapors and turn them into high temperature, high pressure liquids in order to create a lot of heat. You can then either move that heat inside of the home or outside of the home. You can run it in a cooling mode as well, where you're actually reducing the temperature by exhausting that heat with an evaporator or a condenser, depending on which way you're running it. And you can either exhaust that heat inside the home or outside of that home. So with heat pumps, you're able to do heating or cooling. A lot of people are familiar with this. The most basic example is an air conditioning unit sitting outside of your house. That is a heat pump that can only do cooling. So air source heat pumps that can do heating and cooling have a reversing valve, and they're able to run the process in reverse. So instead of pumping heat out of the home, they can pump heat into the home. Now, these systems use an outdoor fan unit as the heat sink, exchanging heat with outside air. With geothermal, it's the same process, the same equipment. However, we bury piping in the earth and use the piping in the earth as a heat sink rather than that outdoor fan unit. The benefit of this is that the earth is at a near constant temperature of 50 to 55 degrees. Meanwhile, the outdoor air temperature is usually the opposite of what you want it to be for its function. So to talk about heating, if you're trying to heat with air source heat pumps or anything using an above ground air exchanger, well, you're trying to pull heat out of 0 to say 10-degree winter air to heat a building. It's a miracle of science that we can accomplish this. It's very doable, but it requires quite a bit of electricity. And if that outdoor air exchange unit is covered in snow or ice, or it just physically gets plainly too cold outside for it to operate, it will shut off and you'll no longer have heating. Now, with geothermal piping being buried under the frost line, that's the benefit of being at least 4 feet deep, if not deeper, is we're in a 55-degree heat sink all year round. So when we want to heat a building, instead of pulling initially from 0 or 10-degree winter air, we can pull from the 55-degree ground. It means we can use warmer refrigerant, and we need to cycle it less often, and overall it uses quite a bit less electricity. One of the main aspects to consider too is that with this piping all being buried under the frost line and no above ground components in this system, it is very unlikely that this system will get shut off by cold temperatures. In fact, during the blizzard of 2022, during Christmas time, our geothermal customers had heat and their systems were running, where the majority of air source customers, their air source heat pumps were not running. So as we get deeper into the heat pump conversation in New York State, we need to start identifying what types of heat pumps we're discussing and incentivizing and which ones make sense in Western New York. Now, the physical components of ground source heat pump versus an air source heat pump. Ground source heat pump being geothermal, air source heat pump being pretty standard Mitsubishi, Trane, Fujitsu, outdoor air condenser connected to air handlers in your home. With those air source systems, again, on the left side of the screen, you can see that outdoor fan condenser. That's going to be sitting above ground outside of your home, probably on a concrete pad or metal brackets. It's usually going to be above the snow a little bit to try and limit how much it's going to be covered in snow or ice during the heating season. But that's your general equipment. You get your outdoor unit that's above the ground. With a ground source heat pump, you have high density polyethylene piping that's under the frost line. So again, we're capitalizing on that temperature in the Earth's crust that's a pretty constant 50 some degrees year round rather than that outdoor fan unit. Now, what ends up being more efficient? We know that air source heat pumps as well as ground source heat pumps can have coefficients of performance over 1, meaning more than 100% efficient energy exchange. We'll dive a little bit deeper into that. But between what's more efficient, we actually see coefficients of performance around 2 to 3.5 for air source heat pumps, but coefficients of performance between 3 and 6 for geothermal systems. So coefficient of performance, what does that mean? It means of how much of the fuel source you're putting through a system, how much heat you're actually getting out of it. So electricity, natural gas, propane, they all have latent thermal content that by combusting or running through electric resistance, you can get that thermal content to come out and expressed as heat. Now, the COP, the coefficient of performance, shows the percentage of that potential energy that's actually converted into heat energy. So for combustion furnaces or boilers, we usually see that 80 to 96% efficiency rating. That means a coefficient of performance between 0.8 for 80% to 0.96 for 96% efficient. What that means is of all the natural gas, propane, heating oil that's being combusted, you're only getting 80 to 96% of that heat. So where's the rest going? You're usually losing a little bit during the combustion process to byproducts. The byproducts you create that gunk up the combustion portion of your furnace or boiler, the combustion chamber. You might have a cracked heat exchanger. This is all where those byproducts go. They coat the interior of your system and sort of gunk it up a little bit. You hope that most of it goes out through your flue or whatever venting you have in your combustion system, but some of that does hang out inside the system. Either way, you are getting almost an entire unit of whatever you're combusting to turn into heat energy, but you're losing a little bit. Now, how is it possible that electric systems have coefficients of performance over 1, meaning over 100%? How is it possible to get more than 100% of something out? Well, that's because they actually had to change how they measure this because of heat pumps. With electric resistance heating, you'd be limited to a COP, a coefficient of performance of up to 1. You can't get more than 100% of the thermal energy that's latent in electricity to come out of it. However, if you're using a heat pump, you're not creating heat from the electricity. You are not running electricity through electric resistance to create heat. What you're doing is you're leveraging heat exchange by using electricity to power pumps, valves, and evaporators and compressors to do the vapor compression cycle. Now, what this means, again, since we're not, for lack of a better term, combusting electricity, we're not taking that thermal content out of the electricity, we're leveraging that energy to have a refrigerant move heat for us, and then we can dump it either in the house or out of the house, hence a heat pump. We're pumping heat in or out of a house through the use of refrigerant and those pieces of technology that we previously mentioned. So when they look at, well, how much heat would we have gotten from just running this electricity through electric resistance versus how much heat did a heat pump running on electricity use? That's where they get, this heat pump is producing 5 or 6 times the amount of heat that we would have gotten from electricity if we were just running it through electric resistance and taking the thermal content of that electricity out. So that's how you end up with coefficients of performance that are so high is, again, we're not taking the thermal content out of the electricity, we're leveraging electricity to do heat exchange. So to show that in chart form, you have heating and cooling graph here showing the efficiencies of different systems based on their coefficient of performance. You can see with a high efficiency gas or propane furnace, that's going to be on the bottom right side of the heating efficiency chart. You can see those coefficients of performance for electric, high efficiency gas or propane, and standard efficiency. Those are all up to or just limited at 1. For all of those, you can't get more heat than what you're combusting, burning, or running through resistance. Now, once you start using heat pump technology, again, leveraging heat exchange with that electricity rather than drawing the thermal content out of it, now you start getting into the barriers of getting much over a 1 COP. Now you're getting a lot more heat out of 1 unit of electricity than you would have if you just ran it through resistance. So I think on the left side here, we have a water furnace, which is our heat pump manufacturer out of Fort Wayne, Indiana. We do use American-made heat pumps that are actually at the top of the line for heat pump technology right now, which is phenomenal. We'll dive a little bit into that a little later. But what I do want to emphasize here is that for both heating efficiency and cooling efficiency, you get geothermal systems at the absolute top of the pack. There is no other way that you can leverage energy and get more return out of it. But the systems certainly do have a price tag to match. And as you'll see, that's because there's quite a lot of work that goes into one of these systems. So the physical components of a geothermal system. You get your heat exchange piping in the ground. This is usually done through a horizontal loop field or a vertical borehole. A horizontal loop field is done where you have a lot of excess land and you can afford, say, a 40-foot by 80-foot footprint being dug up, piping being installed, and then covered back up. That's assuming you have no septic system under that ground. You have no utility lines. You need a free and clear area of land that's at least 40 feet by 80 feet to do a horizontal loop field. In that loop field, you get 80-foot long trenches that are 4 feet wide. And you can sort of see here in that horizontal loop field trench that's uncovered with the slinky loop in it, that's that coiled black piping at the bottom of it. That's a 600-foot coil of piping. So in each 80-foot long trench, you're getting 600 feet of piping. Now, if you're getting 6 trenches in your backyard, that's 4,200 feet of heat exchange piping going at your backyard at 8 feet of depth. That's going to do all your heat exchange for the next couple of 100 years if it's installed correctly. Where we don't have an area that large to install these trenches and all the piping underground, we do what's called a vertical borehole. For the vertical borehole, we have a water well drilling truck come in and drill up to a 500-foot deep borehole. This borehole gets 6-inch wide steel casings put into it until we hit bedrock. Once we hit bedrock and we're drilling through bedrock, it becomes its own casing. So above bedrock, we're casing that hole of steel. And below bedrock, we're using the natural stone of the earth to be the casing and keep the rigidity and structure of that hole. But in that 500-foot deep hole, that's where your piping gets dropped into as a U of piping with a loop at the bottom. So it comes right back up. And then all the empty space between the pipe and the casing is filled with thermally conductive grout. All in all, now that's a 6-inch wide, 500-foot deep heat exchange rod in the earth, essentially. So to give another example of how those go in, I have time lapses here of both the horizontal and the vertical borehole heat exchanger installs. So on the left side, you can see this time lapse going. You can see as the excavator gets to the back of a trench, it looks like some people flash across the screen really quickly. What that is our guys coming over and dropping that 600-foot coil of piping into the bottom of those trenches. The minute they drop that piping in, the excavator starts digging the next trench and uses the earth he excavates from that next trench to backfill the one he had just dug. So to show that one more time, an example, as he finishes the trench he was just digging, our guys come over and lay the piping at the bottom of the trench. And then as he digs the next trench, he is backfilling the previously dug one. And again, that's an area of about 80 feet by 50 feet that he's digging that in. Now, a vertical borehole. We have the water well drilling truck come in, a small excavator to dig what's called a settling pit. The settling pit is for once we hit bedrock, you're going to see a silver liquid coming up out of the hole. That silver liquid is water that we're pumping into the hole to help it cut through the bedrock, and the pulverized bedrock itself that we're pulling up. So again, that silver liquid is nothing more than purely water and pulverized bedrock. But either way, we like to dig a settling pit so all the particulate matter from it can settle into the bottom of it, and it's mostly water content that's coming off the top that we then run into a storm drain, pond, wooded area, wherever the homeowner or property owner prefers. Once that gets to 500 feet deep, they will drop the loop of piping into it. They will grout the hole to fill that empty space between the loop and the steel casings with thermally conductive grout. And at that point, they can start running a water antifreeze mix through the piping to do pressure testing and conductivity testing. This all gets done before the loop is connected to your home or your business to ensure that there's the thermal exchange there that the heat pump will require. Now, connecting that piping into your home or business. Typically, we will bring that piping in 4 feet below grade to keep it under the frost line. So we'll dig a 4-foot deep trench, and at the bottom of that trench, we'll drill 2 small holes through your foundation. We'll put sleeves through there to house our piping and what are called metro seals around those sleeves. On the left side of the screen, the metro seals are those black gaskets that look like they have little silver studs in them around the PVC sleeves. These metro seals will expand or contract with the foundation wall throughout the seasons, so that way there's always an airtight seal. The other 2 photos on this page show that black high-density polyethylene piping coming out of the boreholes and being connected. So this was actually a larger home that needed 2 boreholes. So 2 500-foot boreholes. You can see the piping popping out of the hole at the bottom of the screen on the right, and it's being connected over to the gentleman in the middle of the screen who's connecting it to the second borehole. Once those pipes are fused and you have both boreholes in series, they will bring that piping over to the sleeves going through the foundation wall, bring the piping into the basement where it then can be connected into the heat pump. Once this is all done, we cover it back up, give it a rough grade, and you'd never know that there are 2 500-foot borehole heat exchangers in that small patch of dirt. So this is a home in Amherst, New York. Very, very small yard on the outside of the fence. So this just goes to show how little space you actually need to install Geo. So this is a larger than 3,000 square foot home where they're doing their potable hot water as well as their heating and cooling on geothermal. So again, this is that same property. The left side of the screen is this picture, pardon me, on the left. If you go 4 feet deep, that's where you'd see the PVC sleeves going through the foundation. And the right side of the screen is where the boreholes went. Again, you can see the piping there. So you'd never expect that all this piping is buried under such a small patch of grass and dirt, but it's certainly doable. We do it all the time, and you'd never know from outside the house that it's running on geothermal. Now, the interior equipment, what those pipes get connected to. That's what's on the screen right now. Those are the physical heat pumps themselves. Now, what you have on screen are a hydronic and a forced air version of these. So say you have a furnace and ductwork in your home. You get your heating and or cooling from forced air. Well, we'll remove your furnace and we'll plug in our heat pump to your ductwork in the exact same manner that your furnace was. So on the right side of the screen, you can see that this ground source geothermal heat pump is connected to the ductwork in the same way a furnace would be. It looks just like a furnace, just instead of being a combustion furnace, it's an all-electric ground source heat pump connected to, a 500-foot borehole outside that's housing heat exchange piping. So definitely an intensive system, but it connects into your home in the same way that your previous system did. So the conversion, although it's labor intensive, is actually relatively simple. Now on the left side of the screen is a hydronic system. If you have a boiler and hydronic heat, meaning radiant heat flooring, baseboard radiators, cast iron radiators, etc., you would get a hydronic heat pump. This would plug into your manifold in the exact same way your boiler previously did, and it would continue to heat your radiant flooring, your cast iron radiators, your baseboard radiators in whatever manner that your boiler previously did. Now, there are some nuances here. For example, you're going to be putting water through those radiators at 140 degrees instead of 180 degrees, which 140 is still more than capable of heating the house. However, depending on the amount of heat delivery you have and the amount of heat loss from your lack of insulation, that could adversely affect your heating delivery. So with hydronic systems, we always like to be sure that we're taking care to note what type of insulation you have in the home, how tight it is, both from an insulation standpoint and an air sealing standpoint. So we know, what your heat loss is actually going to look like. But this is all to show that geosystems plug into your home's heating distribution in the same way your furnace or boiler previously did. So when you go geothermal, you don't need to replace your ductwork. You don't need to replace your radiators unless, there's something physically wrong with them. But if they're working right now, then they'll be working with geothermal. Now, the physical heat pump components. This is a forced air heat pump, and on the inside of it, you can see a blower, but instead of having a combustion chamber, there's a bunch of wires and and different electronics, computer, motherboards, you name it. So this is a very smart system, and for anyone who's more engineer-minded, feel free to send us a message after the presentation. We're more than happy to send out spec sheets so you can actually go through all the physical components of our heat pumps. Now, this big push for heat pumps in New York State, where does it come from? Well, it comes from the CLCPA and the general politics around climate right now. So I'm not going to get too deep into where we're sitting with climate. All I will say is that we know something is happening. The Earth naturally goes through cycles of heating or cooling, so it's very tough to say what portion of global warming or cooling is attributed to humans. But what we certainly can say with confidence is that we're not being friendly to our atmosphere. So on the page is a physical representation of the amount of fuel that each person is statistically going to go through in their lifetime. The bottom right of that graphic, you can see what says average person, and it's showing to scale the amount of solid fuel, coal, liquid fuel, petroleum products or gas, and gaseous fuel, natural gas, propane, that they're typically going to go through in their lifetime. You can see it's a pretty solid amount of fuel that the average person is set to go through. And then you multiply that by hundreds of millions of people and then billions of people. And you can see very clearly if that's what we're burning for each person on Earth, we're definitely not being friendly to our atmosphere. We're putting a lot of pollutants up there, a lot of particulate matter, and we are eating away at the ozone layer. We are affecting air quality in especially inner cities, but any sort of urban area. It's not friendly to the air. There's no other way to put it. And by switching to electric systems and cutting down on combustion, we're going to be vastly improving our air quality, as well as cutting down on the safety risks that you inherently have with fuel. When we're transporting fuel under roads, into businesses, into homes, there's always the risk of a fuel leak, explosion, etc. Now, luckily, those aren't incredibly common, but every year they do happen. Every year there are fuel explosions, there are fuel leaks, and lives are lost. It's not, a huge number depending on where you live, but it's not nothing. And I'm sure to each family that has lost someone in an unfortunate accident, it definitely doesn't feel like a small number. So it's just another benefit of switching over to electric is it's going to be better for our environment. It's going to remove health and safety hazards. And it, most importantly, will be using energy that we can actually make at our homes. You can't make coal, you can't make petroleum products, you can't make natural gas at your home or business. And if you can, then you probably don't need us. But what you can do is you can make electricity at your facility. Through wind, through solar, through a lot of different means, actually, you can produce electricity, and a lot of those means are becoming more and more valid and cost effective as time goes on, especially solar. So it only stands to reason, well, if there's a type of energy that we can make on our properties, that's probably what our systems should be running on. So we are at the point where most things are electric, but again, this is one of the last big pushes is the big combustion processes, building, heating, and transportation. We're not touching, the EVs, at the moment, where this presentation isn't about that, but you certainly see them happening. EVs are becoming a big revolution right now, and we're seeing more information come out about hydrogen fuel cell cars, different types of electrolysis, other ways we can power vehicles. So that's coming. I'm not going to put my own viewpoint on it, but I will say is building heating, it certainly makes sense to start switching over from combustion systems to heat pumps. Now, that's on just the logic side of why we might want to switch to heat pumps. Getting into the legislation side, we have the CLCPA. A lot of people have heard of this in New York, but not a lot of people know what it is. So, the CLCPA is the Climate Leadership and Community Protection Act. This was a set of law passed in 2019 to say by 2030, we will have a 40% reduction of greenhouse gas emissions to bring us below our 1990 level. By 2040, we should have 100% emission-free electricity, meaning all our electricity is coming from renewable sources instead of burning or combusting different types of fuel. And by 2050, we'd like to have an 85% reduction of greenhouse gas emissions. Well, how are we going to get there? That's what's being debated right now. That's what they're trying to pass in different bylaws. That's what a lot of different groups are trying to come up with. The how are we going to get here? The CLCPA is the most aggressive climate policy passed by any state in the U.S. So, as New York, a lot of people look to us to be one of the leaders in a lot of different metrics in the U.S., but being a climate leader is something I'm sure that's a little bit new to all of us, especially in the last decade. So how can we meet these standards and these laws without doing anything that's going to be putting New Yorkers in a financially compromising situation or one where they don't have the right type of equipment in their home? One of the ways they were talking about doing it, and again, this is a set of proposed laws, this was not written into law yet, but they would be essentially banning gas systems at different stages. So, for example, in the 2023 New York Housing Compact, Kathy Hochul proposed that by 2026, we would ban the installation of gas systems in small commercial buildings. By 2029, or new construction of small commercial buildings. By 2029, we'd ban gas systems being put in the new builds of large commercial buildings. By 2030, it would be a sales ban of any new fossil fuel powered heating equipment. I mean, anything that's manufactured to be a heating system using fossil fuels after 2030 will not be allowed to be sold in New York. And that'll be equipment that's set up for small commercial or residential buildings. And then that would finally extend all the way up to large existing buildings in 2035. So overall, this wouldn't be necessarily banning gas combustion equipment, period, but by banning the sale of it and by banning the allowance to put it into new builds, you are essentially banning the systems. So this is one of the ways they've talked about doing it. But as you can imagine, a lot of people like their gas systems or their fuel-powered systems and don't necessarily want to give them up in that short amount of time. You also have the idea that, well, if a lot of people still want to have their gas systems, all they're going to do is just go elsewhere for them, whether that means moving out of New York or just driving across the Pennsylvania border to buy gas systems and then transport them back to New York, install them themselves or with a friend or family. Either way, the results might not be ideal. So it might make sense to push these deadlines back a little bit while continuing to incentivize a smart changeover. So either way, even if this was law, you have plenty of time. But I think a lot of the industry people right now are thinking that these deadlines are going to be pushed back a bit. So definitely worth keeping an eye on it. And the most important thing you can do if you don't like the way that New York State is proposing these things is write your elected official. They do actually read these things, whether it's written, called in, emailed. Excuse me. Our elected officials do read our comments. The best point of evidence here is gas stoves. When the CLCPA came out in 2019, all anyone really wanted to talk about was that New York is going to ban your gas stove. Well, gas stoves were part of fossil fuel powered heating equipment. However, after hearing over 35,000 written and called in complaints, for lack of a better term, from New Yorkers, they promptly removed gas stoves from the legislation. So they kept boilers, furnaces, hot water heaters in there, but they removed gas stoves because of how much specifically people wrote and called in saying, we're not ready for our gas stoves to be taken away yet. So the elected officials certainly do listen, and the best way to get their attention is to write to them. You'd be surprised, a lot of people still do this, and it actually has a profound effect. It's much more likely to be looked at than a lot of the other ways you can contact elected officials. So certainly write your elected official, let them know what you think about what's happening in New York and whether or not you like the timeline we're on. Now, how are we doing in terms of these climate goals? Again, talking about the CELCPA, we're supposed to have 100% zero emission electricity by 2040. Well, where do we sit right now? So if you go to NYISO.com, that's NYISO.com, the New York Independent System Operator, you can actually see a real-time matrix of where electricity is coming from. So I pulled it at 10 a.m. this morning, and that mix as of 10 a.m. this morning was 27% of our electricity was coming from hydropower. Wind was accounting for 0.16 of our electric generation. Other renewables, so solar and some of the other fun ones, were clocking at about 3.2% of our electric generated. Nuclear power was giving us a whopping 25.7% of our electricity. Burning natural gas came in at just under 25%. And dual fuel, which is just more combustion, came in at about 18%. Dual fuel is anything else that's burned with natural gas. So if they're burning coal, if they're burning oil, anything else they burn is considered dual fuel. So overall, this depiction is showing that as of this morning, about 43% of our electricity generated in New York State was coming from combustion, and just around 57% of our electric was being generated from renewables, so zero emissions. So by 2040, another 16 years from now, it's absolutely plausible that we could scale up our nuclear, our hydro, our solar, our wind to where they're covering 100% of our electric needs rather than, say, 55% or so. However, they have to take into account redundancy and some of the other seasonality factors that come into electric generation. So leaving the slideshow for a minute, breaking the fourth wall, this is something I like to show people. This NYISO readout changes daily, if not hourly. So you can see real-time changes in this, but this was from November 2023. Just a random reading I had on another day, but it could as well have been a couple days ago. That's how often this changes. And you can see the huge difference between our electric production on these two different days. In November of 2023, on this November 9th at 10:45 a.m., we were pulling about 52% of our energy from combustion, with then less than 50% coming from renewables, instead of vice versa that we had today. Additionally, wind was accounting for something that was actually visible, a good almost 8% of our electricity on this day, where this morning, wind was accounting for less than 1% in a sliver so small we can't even see. So it just goes to show how often these fluctuate. It depends on seasonality. It depends on how we're utilizing energy infrastructure. There's a lot of different things that dictate how and when and why we're pulling energy. But I do like to show this graphic just to say we're actually pretty close to that, what people used to think was an obscene deadline, 100% emission-free electricity by 2040. Well, we're actually well on our way there. It's just going to continue to take more reinvestment and work on our energy grids. So when people talk about the CLCPA, you get a lot of mixed reviews. Some people say it's unattainable. It's certainly attainable. Just the question is, at what rate will we have to continue making these improvements to hit these date deadlines that we've put in place sort of arbitrarily? So hopefully, as the Climate Action Committee is a retroactive group and they continue to reassess the path they're putting New York on, they'll continue to adjust those dates as needed to make sure that we make this transition in an environmentally friendly and financially sustainable way. So now talk about why they think geothermal heat pumps are going to be such a big part of the solution to this equation. Well, we are actually a cooling dominated state. What that means is for our electric grid, we use more electricity for cooling in the summertime than we do for heating in the wintertime. Now, this is expressed by these charts on screen. So looking at 2022, the gray bar is what you might imagine as our energy budget. At any one given time, we could have been putting out, at any one given time, we could deploy 41,000 megawatt hours of electricity to New York State if needed. Now, at what points in the year were we pulling the most energy at one time? Well, in 2022, our winter peak, when we pulled the most electricity at any one given time during the winter, I believe came in late December or early January. But either way, that peak load was 23,000 megawatt hours. Now, that is solidly under our 41,000 megawatt hour capacity, but it, is certainly not as high as our summertime peak, which was 30,500 megawatt hours. So again, that's because we're using a lot more electricity in the summer rather than the winter, because everyone's AC runs on electricity. Not everyone's heat runs on electricity. So that's why we have higher usage in the summertime. Now, people might say, 30,000 megawatt hours out of a capacity of 41,000. We still have plenty of electricity. No need to worry here. Unfortunately, even though we might have the electric reserves to put out 41,000 megawatt hours of electricity, our capacity for transmitting this electricity seems to be limited in the low 30,000s. And what I mean by that is in that summer of 2022, when we went over 30,000 megawatt hours of electricity being deployed at one time, we started to see problems with our distribution grid, meaning distribution lines were maxed out with the amount of electricity that they could carry. And if we started calling for more, trying to push more through them, we could have ended up with rolling brown or blackouts like you're starting to see in Texas and California. So that's a very important point that we can't make enough, is that more work needs to be done to this electric grid. Right now, we can't even deploy all the electric we hold in reserve if we wanted to. So it definitely shows the importance of bolstering our grid as we do this push towards electricity. Now you see the next year in 2023, our wintertime electric peak was within 2 megawatt hours of the previous years, the difference in 23,237 and 23,235. So I think that's definitely very interesting. But look at that. In the summertime, our electric peak was actually lower by a decent margin than the 2022 one. You could say it was just because it was a milder summer and people didn't need to air condition as much, but arguably I think it was actually a hotter summer. Someone can correct me with that, but I believe the average temperature was warmer. So why did we use less electricity? Because there was a lot of literature going out on using less electricity, altering your set points, not running your AC or your lights as much. And I think we've all seen those little tips and tricks come through in the mail, online. It seems like not just the grid, but other groups are promoting these tips and tricks too. I know we are here at NOCO. Well, that's because the grid knows how important it is to drop that peak load down. Again, at around just over 30,000 megawatt hours, we were having trouble transmitting it. So in the meantime, while we work on bolstering our transmission capabilities, we also need to work on limiting how much electricity we use when we don't need to be using it. So to tie this back into geothermal, the reason they think geothermal is going to help this is something called peak leveling. So you can imagine that blue bar and that orange bar trying to meet in the middle, with the blue bar going up and the orange bar going down. Well, how we'd accomplish that is if people are using geothermal, they're using more electricity in the winter time because they'll be using electricity for heating rather than, say, natural gas, heating oil, coal, propane, wood, you name it. So that would increase that blue bar, the amount of electric we're using in the winter, but it would decrease the orange bar. And that's because everyone already has their AC running on electricity. And geothermal systems use 80 to 90% less electricity than traditional ACs. Your normal AC is probably using somewhere between 2,000 and 4,000 kilowatt hours of electricity during the summertime to do your air conditioning. The geothermal system will do the same amount of air conditioning for, say, 400 or 500 kilowatt hours. So we're going from thousands of kilowatt hours for AC for a single home to hundreds. So by lowering that orange summertime peak and raising that blue wintertime peak, we'd be doing what's called peak leveling. This is a lot better for the grid to have a more standard amount of energy that they're consistently pushing through it. But also overall, by lowering our highest peak, which is again that orange, that summertime peak, by lowering that peak, we could lower the amount of electricity that New York State has to keep on hand for us. Over time, this will certainly go up in the long term, but managing it in the short term is important as we continue to work on the grid and our transmission and storage capabilities. So in general, some of those tips and tricks to cut down on your energy usage period, even if you don't replace your heating system with geothermal. You can upgrade your insulation. If your home is retaining more of the heat or the cooling you're putting into it, you'll need to use less energy overall and you'll have a more comfortable home. You can alter your set points. For every set point you go above for heating or below for cooling, you're actually using exponentially more energy. So, each time you click your thermostat up 1 degree for heating in the winter, it's not using the same amount of electricity to bump it up, or the same amount of natural gas to bump it up 1 degree. As you go hotter and hotter, it uses exponentially more energy. So by just lowering your set point from, say, heating to 68, heating to 65 or 66, that alone can actually cut a disproportional amount of energy out of your bill. Same with air conditioning. Instead of cooling your house to 68 degrees, cool it to 74 degrees. You'll certainly still feel cool because it's a lot lower than your body temperature, but you'll save a lot of energy by having your air conditioning set to somewhere in the low or mid 70s instead of the 60s. You can put in solar or wind systems so you can start producing electricity at your own home. Solar systems alone have come very far in the last couple of decades. They've already more than doubled the amount of wattage power they have just in the last 10 years alone. And they're, for the majority, they're all set to be still running at 90% efficiency at year 25, meaning you get at least 25, not more, good years of solar production out of panels these days. I actually have solar panels on my house, and I haven't had any sort of usage electric bill in years. I'm not kidding. My bill is about $18 from the grid every month because I'm making all my electricity with solar and I'm just paying for my connection fee. I'm putting geothermal in my house pretty soon, so I can start capitalizing on my low cost of electricity as well as cutting down the energy I need, but we'll dive into the numbers a little bit more in later slides. Finally, for your last tip to make your home more efficient heating and cooling systems. If you go from something like a natural gas furnace using a decent amount of therms and natural gas throughout the year for heating, and then a whole home AC using a few thousand kilowatt hours of electricity for cooling, well, you can switch to a geothermal system and be using, say, 4,000 kilowatt hours of electricity to do your heating and your cooling throughout the whole year. And yes, I said that correctly. The amount of electricity you're typically using just for an air conditioning system, that's usually the amount of electricity you'll use for a geothermal system to do heating and cooling instead of just one of them. So we can essentially cut out all the energy that went into heating, because just the energy that you use for cooling can now do your heating and your cooling. It's that small amount of electricity that Geo needs to operate. And that's because, again, we're not forcing this heat exchange with the outside air that's at unfriendly temperatures. And we're not throwing a lot of electricity through pumps and evaporators and compressors to get the desired heating or cooling effect. We're still doing that process, but we're letting the earth do most of that heat exchange for us. Instead of pushing hot, air from a home into 80, 90 degree summer air with an air conditioner and air source system, we are pushing it into the 50 some degree ground. Instead of having to force that hot air to accept more heat, we're letting the earth naturally pull the heat out of our homes because it's 50 some degrees. It's more than happy to absorb the high 60s, the low 70s, maybe even the low 80s, the heat that's coming out of your home. Well, it's at a lower temperature. It'll naturally pull that heat out. All we have to do is move that heat with refrigerant. So geothermal systems in a nutshell are letting the earth do our heat exchange for us and saving us vast amounts of energy. So we did just talk about this for a decent amount, but I have some of those metrics restated on the screen. Again, geosystems use a fairly small amount of electricity, especially when compared to what a conventional AC uses or the amount of fuel that's going into a heating system. So how popular is geothermal? How are these installations coming along? How much is it being utilized in New York? Well, on the left side of the screen, you can see a map that has different dots representing how many tons of heating and cooling are being installed with geothermal throughout New York State. As you can see, it's actually going on throughout the entire state in pretty large numbers, but there's a huge concentration down in New York City. Now, the reason there's a huge concentration down in New York City is because of sunset fossil fuel laws. New York City is expected to get off combustion systems for heating before the rest of the state. So they've evaluated their options. They see that clearly geothermal is by far the most energy efficient way to do this. These are building managers who know how much energy their buildings use and know how much money it costs and how much they can save by cutting down on that energy usage. And so they've all done the math. And it looks like for all the different types of electric systems, they could replace their heating and potable hot water and cooling systems with. Geothermal is far above and beyond the most efficient and costing the least amount to run, but also the least amount to maintain. Geothermal also cuts down maintenance costs by a huge amount. And again, by removing the combustion process, you no longer have gunk going into the interior of your system, gunking it up, and meaning you need service calls annually to clean out that combustion chamber, maybe exchange components that have gotten too gunked up or aren't working well anymore. And you still have to exhaust that byproduct outside of the building through ventilation. With geothermal, there's no byproduct waste to exhaust. There's no combustion chamber to clean the byproducts of burning fuel out. It's actually a fairly maintenance-free system. So beyond the operational savings of using such a low amount of electricity to operate it, there's also those maintenance savings. So we're seeing property managers switch to geothermal, and these are guys who it's their business to know everything about their buildings. So if New York City is any indication, this is the revolution that's coming. If you have a geo system, you're not subject to outdoor temperatures or conditions. You're not worried about snow covering up your outdoor air exchanger or your vent pipe for your combustion system. Now, again, what's that thing they tell all of us during blizzards? Check your vent pipes, make sure they're clear. If they're filled with snow, then the byproduct can't escape from your heating system. It's backing up into your heating system. And now you have noxious gas being pushed into your home, as well as your heating system being shut off, since all of them come with modern safety features now. And if they sense, any sort of dangerous gas backing up into the unit, well, it knows it's not exhausting it to outside, and it's going to shut off so it doesn't explode. So now you have no heat and you have gas backing up into your home. And this is all in the middle of the winter when you need it the most. With geosystems, you don't need to worry about that. There's no vent that can get clogged up with snow. There's no exhaust byproduct that needs to be sent outside the home. There's no outdoor air exchanger that can get covered in snow or ice. Everything is buried under the frost line and it goes into your house in the same manner. And it's all electric, no combustion. So for all these metrics on top of the operating efficiency, that's why we're seeing such a big push for geothermal, not only from the state legislation, but to the state building owners, all the way down to state homeowners. So now talking about this in Western New York. So National Fuel actually has to do a utility thermal network in Buffalo to show geothermal's feasibility. They were originally looking at doing the Northland Training Center as well as 11 residential homes north of it. This utility geothermal network would mean that geothermal heat exchange pipes are buried under the road in a sense very similar to most utilities, rather than each building having its own piping. The benefit of this is theoretically you can have utility companies, who are already experienced with digging up roads, installing large networks underground. You can have them start to transition some of this older infrastructure that we're not going to be using anymore to geothermal networks, or at least replacing it. So I don't think the Northland Training Center project is moving forward due to feasibility studies. National Fuel is currently looking at other job sites. We wish them all the best. And hopefully we'll see some cool projects coming out of National Fuel and maybe even National Grid in the next few years as they continue to explore alternative energy. Now, the overall benefits of geothermal. Cost effective. Now, these systems, again, you're going to go from spending, say, $1,000 a year of electricity on your air conditioning between all the summer months, and $1,000 or more on your heating during the winter, from say 1,000 on natural gas, 2,000 on propane, 3,000 on heating oil. Whatever you're spending, it's probably north of $1,000 a year. When you switch to Geo, you're typically going to end up spending somewhere in a few $100s of electricity for your heating, cooling annually. That means no more monthly bills of over $100. You're now going to be looking at monthly bills of around $20 to $80 in the worst of the months. Overall, probably adding up to somewhere in the $400 to $600 range rather than a couple $1,000s. So, we're cutting down on the energy used for heating and for cooling by a large amount. And, saving even just $2,000 a year, that payback period fills up pretty quickly. Energy efficiency. Again, geothermal systems use 80 to 90% less electric for AC, and over the different types of heating systems, they're more efficient by 60, 80, 90%, depending on the heating metric. Comfortable. What a lot of people don't know about geosystems is they actually constantly run. They're set up to constantly keep your home or business within half a degree of your set point, and that's part of the efficiency. So they're constantly running in a low stage when they're at their desired temperature. Versus current systems where they get a reading from your thermostat saying, hey, we're above or below the desired set temperature. We need the AC, we need the heat to kick back on and bring us back to our set temperature. It's sort of like starting and stopping a car and turning it on and off at red lights. We don't like to turn our cars off at red lights, even though theoretically it would save us gasoline. Well, why don't we do that? We don't do it because it actually costs more gasoline to start the car and get it running than it would have just to let it sit and idle for, a minute or two at the stop sign. It's the exact same idea with your heating system. By having it constantly run at a high efficiency stage is actually using a lot less fuel and energy than constantly starting and stopping. So on top of, just being another reason it's more energy efficient, it actually keeps your home more comfortable because you never get more than half a degree outside of your set temperature. Quiet. Geosystems are actually a lot quieter than typical ACs and furnaces. So you won't hear it kicking on in the middle of the night, which is really nice. Environmentally friendly. There's zero combustion that goes on with this type of system. So you're not putting any byproduct out into the environment, and you're using a lot less energy than any other system. So in both those ways, it's better for the environment. System longevity. Again, because of no combustion, no combustion chamber, no heat exchanger to crack. You're not putting that intense burning of fuels inside a compartment. You're not doing that inside your home anymore. Well, that means the system's going to last a lot longer. There's a lot less wear and tear on it. You're likely to see your geothermal system last for easily over 30 years rather than current furnaces and boilers that seem to be kicking out at around 15, 20 years. Clean air. Geosystems typically have more active dehumidification than normal AC systems, and that's just simply because the piece of metal that makes contact with the air to draw moisture out of it, it's just a bigger piece of metal in geosystems. Some more surface area contact with the air means more dehumidification, but we also put in standard MERV 11 filters with Geo. That's one step below hospital grade air purification. And we do that just to put that extra level of cleanliness in your home. Now, that isn't to say you can't buy a MERV 11 filter for your normal furnace, but usually these filters are a little bit larger than what your normal furnace will allow. So the bigger filter capacity for Geo lets you do more industrial and more serious air filters that filter out a higher level of particulate matter. Flexibility. With a geosystem, you can both heat and cool from the same unit rather than needing two different units. Safety, by not having gas piped into the unit or oil or propane, you're no longer burning things inside your home. There's no risk of fire or explosion. There's also no risk of gas leaks or carbon monoxide poisoning from fuel coming through a fitting into your home. Fittings do break down over time. It's the important part of getting your system serviced, so they can also check whatever gas or oil connections you have and make sure nothing's leaking. Then finally, less obtrusive. Because everything's buried 4 feet underground or inside your mechanical room, there's no outdoor fan unit, there's nothing you can see from outside, no vent, nothing that's on the outside of your house. Now, the meat and potatoes that most people are interested in, all the incentives they have out for geosystems. Geosystems are pretty expensive installs, as you can probably tell from the slides we've gone through showing what physically has to happen for a geosystem to be put in. Thousands of feet of piping in the ground outside of your home, connected to your home in a safe manner with an entirely new set of mechanicals. Well, it is an expensive installation, but because New York State knows how much that's going to help us with not only our energy bills, but our energy requirements, they're putting some pretty serious financial incentives out there. The first is a clean heat rebate. It's $1,500 for every 10,000 BTU of system size. So say you're getting a 50,000 BTU unit. Well, that would be 5 times $1,500. That's a $7,500 rebate. That comes right off the top line cost. You don't need to pay it. National Grid will pay it for you. Or NYSEG, it really just depends on which electric provider you have. But both NYSEG and National Grid offer the same amount. The federal tax credit. Now that is 30% of the entire system's cost. Now, they will send it to you just like a solar check after you file for geothermal. They'll send this to you in a check during your tax return time, and you'll get essentially a tax return check for whatever amount you file for. Same with the New York State tax credit. That one unfortunately caps at $5,000. But you know, that $5,000 from New York State and say 10, 15 plus grand from the feds, being a non-refundable tax credit, you will recoup all that money. But just the question is, how long will it take? And what I mean by that is both New York State and the federal government will not send you a larger check than what you paid in taxes. So say your New York State $5,000 tax credit. Well, if you pay at least $5,000 or more a year to New York State in taxes, they'll send you that $5,000 check in one lump sum during your next tax time. Say you only pay $2,500 a year in New York State taxes. Now it'll take you 2 years to recoup that $5,000 because they will not send you more than you're currently paying in taxes. Same goes for the feds. If you're going to get, say, 15 grand from the federal government for your geosystem, well, you'd need to be paying at least $15,000 a year in federal taxes to recoup it all in 1 year. If you're only paying $5,000 a year in federal taxes, it'll take you 3 years to recoup it. So we certainly recommend consulting with your financial professional, whoever does your taxes, so you can know, hey, am I getting all this money back in 1 year, or is it going to take me 2 years or so on? Commercial and nonprofit incentives. Well, these actually get really fun because you get extra things like an additional 10% with no cap taken off the project because we use domestic content. We use heat pumps made in the US. Energy property is depreciated on a 5-year schedule rather than a 30-year schedule. In 2023, that depreciation was 80% in year 1, with 5% depreciation following in the next 4 years. And now you've depreciated 100% of the system in 5 years. I believe in 2024, the year 1 depreciation dropped down to 60%. So it'd be 60% in 2024 and 10% in each year after. But we can give more specific schedules of this based on your building or your geo quote if you're commercial. So that's just naming a couple of them. There are even more, but we'll get into those as case-by-case basis as we discuss specific geothermal projects with any building owners or homeowners. Now, what does the actual pricing look like? So on screen, we have an example of a system that's going in pretty soon. The top line of this system is $48,450. There's an extra 4 in there. So that looks like actually way more than it should. It looks like $484,000. My mistake. There's either an extra 4 or an extra 0 in there. But either way, it's about $48,500. So definitely a huge amount of money, something that probably wouldn't be affordable for a heating system on its own. However, that clean heat rebate takes off $6,700. So now around $41,000 needs to be paid or financed rather than $48,000. And then after that number is paid or financed, this person's going to receive over $12,000 from the federal government and over $5,000 from New York State. So that $48,000 plus project, the government's going to be paying for $24,000 of it, leaving the homeowner with a $24,000 end of the day bill as well. So still definitely a lot more expensive than a traditional boiler or furnace. But if any of you have looked into air source heat pumps, this is actually around the price you can expect to pay for air source heat pumps. They're easily in the low 20s to the low 30s. So, if you're looking at heat pumps and you're looking at spending 20 to 30 grand regardless, go with the system that actually runs year round and uses far less electricity. But beyond that, one of the important things to consider here is that if you need to replace a heating or a cooling system, you're already out the better part of 10 grand, if not more. If you need a furnace and an AC replaced and you want a high efficiency one of each, you're spending easily $12,000, $14,000 with install. So systems are a lot more expensive in general than they used to be. Geo is certainly a good 10 grand more expensive than, your traditional furnace or boiler. However, if it's going to save you, say, 2 grand on your heating costs next year, taking you from a $2,500 spend to a $500 spend, it's going to do your AC with that and save you another grand in AC. Well, if you're saving a couple grand a year, paying an extra 10 grand for your heating system is a good move because you're going to make that money back in 5 years. And now for the next 25 plus years, the system's alive, you're going to be spending a lot less than your neighbors and a lot less than you would have otherwise. These are sunk costs people don't think about. They'd much rather pay 8 grand up front and then $4,000 a year to run it for the next 30 friggin' years versus paying, say $25,000 up front and then spending $500 a year for the next 30 years rather than a few grand. Obviously energy costs change over time, but that's another important point to look at. Electricity is increasing in price slower than fuels are increasing in price. The gap between them is widening. By staying on combustion, you're guaranteeing to continue spending a lot more a year, on top of having a system that's a little bit less reliable. So with geothermal, even though it's certainly a pretty big bill, there's a reason that the government's willing to spend so much money to cover parts of it, is they know that this is going to help people manage their energy better, spend less money on energy, and most importantly to them, be less intensive on the grid. They'll have to have less electricity and energy in reserve for us, and there will be less of a strain on the grid in the summertime from all these inefficient AC systems. So to get into an actual example, we have a customer here where his top line price was $41,500. This is pretty much some of the lowest pricing you can get for Geo if you have the room for a horizontal loop field and if you have a system that's ready to be swapped out. This gentleman got an $8,500 clean heat rebate, bringing his total cost payer finance to $33,000. He was not eligible for the New York State tax credit, unfortunately, which would have brought his costs down by another 5 grand. But even without it, that federal tax credit brought his total all-in cost for Geo down to $19,500. Well, before that, he was using fuel oil. He used 675 gallons a year, and in the year that he went geothermal, the average cost of heating oil in his area was $5.19 a gallon. If he had stayed on geothermal in 2023, he would have spent $3,500 on heating his home. Instead, he went geothermal at the beginning of the heating season, and from the monitoring equipment on the Geo system, we know exactly how much electricity it used. Well, his system used 2,618 kilowatt hours of electric to do his heating. Well, overall, that ended up costing $418. So he saved $3,100 by going geothermal. Considering that $19,000 Geo system was about, let's call it, that's about 6 grand, 7 grand more than he would have paid for a high efficiency total boiler replacement, but let's just call it 10 grand. Let's just say it's 10 grand more than he needed to spend. Well, saving $3,000 a year puts his payback period at about 3 years for that overage he spent on it. His payback period on the system overall, assuming he didn't need to replace it at all, let's just call that whole $20,000 on Geo, sunk cost. Well, his payback period on that's only about 6 years. He's saving so much money that the overage he spent on Geo is easily justifiable. And now as he goes through the next few decades of heating, he's going to have a continued obscene amount of savings because he's not going to be spending 3-4 grand a year on heating anymore. Now, how efficient are these geosystems? What can you really expect to spend on them? Well, like I've been saying, a few $100s. On screen is a chart of what geosystems in our areas actually are currently using. I have this chart broken down by heating and cooling systems. These are all forced air systems, so I can show cooling as well, since obviously hydronic water heat systems do not have a cooling aspect usually. But you can see on here on the left columns, you have the total amount of electricity and the total costs of that electricity. And then that's broken up by the heating portion and the cooling portion. So again, we're talking hundreds of kilowatt hours through the AC through a whole summer rather than thousands. We're talking about, 10 to 20 bucks a month in the summer for your AC. For heating, we're talking a few $100 instead of a few thousand. We're talking, a monthly heating bill of $80 versus $220 from National Fuel. So your heating bills and your cooling bills do both drop significantly. Just the question is, how much they're going to be saving you enough to justify the extra you'll spend on geo. A lot of cases it is. Some cases it isn't. So what we do is we come in, and if you're interested in looking at geo systems, we'll assess your home or business for geo. We'll let you know what the cost is and what the transition would mean, both physically and in terms of your energy usage. And then you can decide if you want to go deeper or not. We don't charge for that consulting. We don't charge for that site assessment. We really do treat this as an entirely educational venture starting out. So feel free to reach out to us. And even if you're not planning on buying anything at all, we're more than happy to show you what a conversion to geothermal would be, both so you know what it would cost and what physically would be required, and also so you're ready in the future for when inevitably this continues down the path of whole market acceptance. Now, in general, again, just to go over those general heating metrics on the right side of the screen, you have how much people are typically spending with each type of energy to heat their home. If they have electric resistance heat or an air source heat pump, they're probably spending almost around $2,000 in electric. If they have natural gas heating, they're probably spending, mid 1,000s, $1,200 to $1,800 a year on natural gas. And again, these are all for quote unquote average sized houses. So we're talking around 2,000 square foot homes here. On propane, it might cost them $2,500 a year to heat it. And on heating oil, it could be as high as $4,000, $5,000 a year. In general, electric AC for that size house is usually going to be around $850 worth of electric. Now looking at geo, it's going to use about $450 worth of electric to heat your house and around $140 worth of electric to cool your house. So in total, you have an all-in spend of around $600 for heating and cooling versus thousands on any other heating metric. So the savings are always there with geosystems. Just the question is, are the savings high enough to validate putting in, a more expensive system? It's going to last longer. You're going to have more comfortability and more reliability with it, but it has a price tag to match. And again, we pride ourselves at walking you through that conversation, being objective. We'll put all the facts and figures out there for you, and then we'll back off. We'll leave you alone to make your own decision because, again, the educational piece is the most important right now as New York State continues to go down a multi-year path into energy efficiency and heat pump exploration. So that is the end of the presentation. We definitely ran over time a little bit. So for those of you that are still with us, I really appreciate you sticking with the presentation this long. If you have any questions, feel free to throw them in the chat. I'll hang out for a while and answer anything that anyone wants to put in there. But otherwise, thank you guys so much for attending. We really do appreciate the interest in geothermal. And if you want some sort of assessment for your home or business, you can reach out to us either through my own phone number or through, bposner@noco.com is my email, or you can just go to noco.com, noco.com, and there's a lot of different ways to contact us. But again, thank you everybody so much for attending, and hope you have a fantastic day.